All right. Welcome, Internet, period 3, period 7. This is discrete math. Here's where we're at. There are no juniors here because of some AP exam. What's been going on in this class? Lots of graph theory. I believe what we did last class was... Yeah. First we did a proof that fully characterized Euler circuits, and we said that there is an Euler circuit if and only if your simple graph if and only if your graph has no vertices of odd degree, and an Euler trail if and only if there are exactly 2 vertices of odd degree.
Those are edges.
What's up? That was the Euler one.
Yep.
There's a lot of vocab. It's hard to keep straight, but I can do it. So you have an Euler trail. What is a trail? ET for VP means a trail does not repeat edges. So an Euler trail is a trail which uses every edge and does not repeat any edges. Thus, every edge is used exactly once. An Euler circuit is a circuit. First of all, what is a circuit? A circuit is where you
go back to the start.
You do not repeat edges and you finish where you started. So a Euler, a closed trail.
I just heard you say vertices instead of edges.
Did I say the wrong thing?
I think so.
It's very possible. And so a Euler circuit is one in which you use every edge exactly once and you end where you started. So that was pretty fun. In the second half of class, we talked about Hamilton paths and Hamilton cycles. A path is one in which you do not repeat vertices, and a Hamilton path is one in which you use every vertex. And finally, a Hamilton cycle is one in which you go all the way around, ending back where you started, and not using any vertex more than once, and using every vertex. Okay, good. So we also had some homework on that topic, which was due last class, which we did not go over, and we will still not go over today either, because people aren't here. So we'll do that next class. And there was no homework due today, so we're ready for fresh learning. Are you ready?
Yeah.
I am ready. Good. All right. So let's kind of talk about this. We have been talking about graphs, and we took much effort once upon a time to define a graph precisely as a set of vertices, edges, and some function which maps you from vertices to edges. But we also have been just drawing these things, and we've been pretty casual about the relationship between our graph and our pictures. But sometimes you have different things that don't look the same at all. For example, here we go. I'll just pick an example. So this might be A, B, C, and D. And this is a picture of the relationships between the vertices and edges. But I could also draw a kind of different picture. And this is A, this is D. Okay, is this the same graph? Is this the same graph?
Yeah.
Yeah, it is. Okay. So what we refer to this as an embedding of the graph, and this is another embedding of the graph. And embedding is just like a picture. And so the graph itself is defined just by the actual set of vertices. In this case, it's A, B, C, D. This is V. And the set of edges is just whatever they are. Let's just say because this is a simple graph, I can just get away with saying A, B, A, C, B, C, B, D, and C. Okay. And both of these have this. So, okay, the point is, I guess, that you can have two pictures which look quite different, but are in fact just the same graph. All right, and in fact, you can have totally different graphs with different sets of vertices, but which like basically are more or less like the same kind of thing. So, actually, before we get to that, because I want to talk a little bit about like computer science a little bit today, because we've been doing like, so how did you know that this was the same graph? Yeah.
You can like make all the do the functions and then like see if like the functions are the same.
Yeah, actually, hold on. Let me give my actual example first, and then we'll go back to this, because this is like actually the same graph. But what you often find is like, okay, here we go. Let's make let's do this picture. So here we have A, B, D, C, F, and an E. And I think I need one more. Looking so good. Okay, that's a graph. And okay, cool. And here is another graph. And yeah. So X, Y, W, U, Z. Right. Some of you are already like know what to do like before I even ask the question. Well, these are technically not the same graph because they're just not the same graph. Their sets of vertices are totally different from each other. Their edges are totally different. Yet, like
They share graph-like properties.
they share graph-like properties. What's up?
Does Y go to Z?
Does Y go to Z? No.
No. Okay. Because B doesn't go to
Okay, so what would we like to say about these two graphs, however? They're like basically the same, man. Yeah, let's use simple language first, then we'll add technical language as we need to. Jesse, can you explain why they're like basically the same?
If you think of like A or E, B, D, it's like a triangle. It's kind of like folded over. If you like unfold it and then shift the vertices around, they look the same.
Yeah, that's right. He's saying like, dude, if the graph is just defined by the vertices and which vertices are connected to each other and how many times, then like if you just move the vertices around, you don't change any of those properties. And in fact, that these edges are like straight lines is also just irrelevant. That's just a picture. And also like if you just move, it doesn't matter. Crossings, they're all like irrelevant, right? So I think what he's doing is saying he's just mentally, take this point E and just like move it up there and kind of like shake things around a little bit. This is basically just the same graph. All right, so yeah, we don't want to waste our time analyzing like the same graph over and over again. So we want some kind of vocabulary to explain what it means for these two graphs to be essentially the same. What we say is they're isomorphic. This is a word that came up in logic and also probably comes up in like other contexts. You guys are abnormally well informed on all kinds of topics. I mean, who's never heard of this before? Have you ever heard of an isomorphism? Wait, really? Like in what? Like where?
Short says
isomorphism
like
weekly. It's like everywhere.
Okay, apparently Schwartz talks about isomorphisms weekly, so that's good. Yeah, we need to move a little bit. So what's an isomorphism? Well,
Isolated morphism.
an isomorphism is it's a mapping which shows that two graphs are isomorphic or essentially the same. So in this case, the mapping would match points together, which are basically just the same point. And in here we kind of have B and Z being the same, I think is how Jesse was thinking of it. These two are the same. U, this picture's going to get ugly, and A and U are the same. D and W are the same. And C and X are the same, and F and Y. In other words, the second graph is really just a relabeling of the first graph. Okay, back in logic, I talked about this with, I think I talked about this, that it's like a remake of a movie. So if you have a movie, the classic example in the literature is Mean Girls, which is 10 years old, takes place in high school. Have you seen Mean Girls?
Of course.
Of course,
It's not
yeah.
10 years old.
It's,
13 years old.
damn, it's getting pretty old. So, it's a really good movie, and it takes place in high school what's nice about it is, it has many characters, all of which have different relationships to each other. If you've never seen the movie before, it's a high school, there's some mean girls, and so you have all these people, some of them are in love with each other, sometimes those loves are reciprocated, sometimes not. Some people are friends with each other, some people are enemies, there are some frenemies, and it changes a little bit over time. But you have a basic structure. So you could represent this with a graph, of course. And you'd have to have different colored edges for the different kinds of relationships you can have, and you'd have to make it time dependent and whatever. Alright, so suppose now we would like to remake this movie, but not pay any royalties. So we better try to disguise it as much as possible. So it's Russia, you're remaking the movie, and so you make it with cartoon dogs. Didn't I do the same example in logic? Yeah.
Yes.
Yeah, so you good that you guys are laughing the second time you heard it. All right. You remake Mean Girls with Russian cartoon dogs, and what you do is for every character in Mean Girls, you have a dog, and some of the dogs are mean to each other, some of the dogs like each other, and they express their love in different ways. Butt sniffing versus hanging out in the mall or whatever. But it's all basically the same thing. And if you're watching, if you know Mean Girls very well, and then you're watching this remake, this would be good to become the classic YouTube video on isomorphism. If you're watching this movie, and it's all these cartoon dogs, they're speaking Russian and subtitled, somewhere around the half-hour mark, you're like, wait a second, this is just Mean Girls. Just transferred to the world of cartoon dogs. There's the same exact relationships, the same people who are friends with each other, then they're enemies, and then there's love, and there's reciprocated, it's not reciprocated, etc., etc. Okay, so, what does it mean for these two movies to be isomorphic? It means that you can have a function mapping each of the characters from Mean Girls, the humans, to one of the cartoon Russian dogs in such a way that if two people in the original have a certain relationship, then the two cartoon Russian dogs who are playing those same characters are also going to have that same relationship. Follow? Okay, so the formal definition is exactly the same. So if G is a graph with a certain set of vertices, a certain set of edges, and the phi function mapping edges to vertices, and you have a graph G prime, which is V prime, E prime, phi prime, then we say G, so then we have, there's this Greek letter that I can't quite do very well, so I'm just going to use I. I is an isomorphism between G and G prime, if and only if. What's up?
What Greek letter are you trying to do? Or
It's so hard. It's zeta. It's like.
Oh yeah.
Oh, it's like.
Yeah.
I guess I should just keep doing it until I get better.
Practice makes perfect.
No, I don't.
Says the people
No.
who do
Good.
practice.
I like this great. Zeta perfect one. It's not perfect. It's like you practice it wrong.
Like that.
That's terrible.
Wow.
It's so hard.
Zeta.
I don't even know what zeta is supposed to look like. But
Okay, good. That's my zeta. Take it or leave it. It's pretty good. Okay, zeta is an isomorphism between G and G prime. If and what's wrong?
No, yeah,
It's pretty good. Yeah. If and only if VI and VJ are adjacent in G if and only if of VI and of VJ are adjacent in G prime. So this is a mapping. I should probably say more things about this one. It is a function. So it's a bijection between the vertices. Stop throwing the stupid green thing. Is a bijection between V and V prime. So what we do is basically zeta is this mapping over here in red. Formally, zeta in this case would be just the function which takes you from, which says, match A with U, match B with, I'll be honest, we can do this fast, B with Z, C with X, D with E with, and F with
Y.
Okay. So that just is the bijection. This bijection is an isomorphism if it just preserves relationships. In this case, there's only one relationship, unlike in the real world of high school, there's only one possible relationship the two vertices can have in graph theory. They'll either have an edge between them or not. Okay, so so that's an isomorphism. Hey, how do you actually check to see? Oh, so this is an isomorphism, and we say the two graphs are isomorphic if there exists an isomorphism. All right, how can we tell if two graphs if two graphs are isomorphic?
Make an adjacency matrix.
Yeah, so this is hard, right? What's like the stupidest check? What's like the simplest possible thing you can do to check to see if two graphs are isomorphic? Yo.
Well, if you relabel all the points.
No, even simpler than that. What's the simplest possible way?
Look at them and see that they look the same.
Are they the same thing?
Okay, so we have. Yeah, that's a good one. Okay, so we actually need to answer this two ways. Are we humans or are we computers? So if we're humans, then just look at it is going to be pretty good. And then what's one way in which you could just look at it and decide that they're not isomorphic?
They have different amounts of vertices or edges.
Okay, all right. So yeah, good. If as the isomorphism is a bijection, if there are like not even the same number of vertices, then just forget about it. Are you rotating as needed? So that's like check number one. Is like are there the same number of vertices? So like whatever. I'm not going to bother writing it down. Okay, check number two.
Same number of edges.
Are there the same number of edges? Yeah, we could also just check to see if there are the different numbers of edges, then this is just not going to work at all.
Are there the same numbers of edges?
Yeah, well that's the next check.
Yeah, I know, that's what I'm jumping to.
What is he trying to say?
Like same
Like
numbers,
for-
like the highest amount of edges has to be the highest amount in the other one.
Like the degrees.
The degrees,
Yeah.
the degrees all have to be the same.
Yeah, the degrees of the vertices.
Yeah.
Yeah, that's right. Yeah, that's right. And if these two graphs have any chance of being isomorphic, then this isn't even count. Over here, let's look at these two. If I call this graph G and this graph G prime, yes, the picture's getting messed up with the extraneous red graph, but we can create the so-called degree sequence. The degree sequence is a non-increasing list of the degrees of all the vertices. So what's the highest degree vertex in this graph?
3.
4.
There's a 4. Yeah, there's one of degree 4. What's the next highest? 3. And then there's like another 3.
There's two.
Yeah. So 3, and then it's like 2, 2, 2.
Wait. Keep track of the degrees. Keep track of what nodes have.
No, but that would
Wait, well this is just the first check. Like the easiest thing you could do is just check all the vertices, then check all the edges. Then I thought this is what you were talking about, right?
Yeah.
Go through the edges and see the degree of go through all the vertices and see the degree of each vertex. And then of course over here what do we get? Is there a vertex of degree 4? Yeah, there is. If there were no vertex of degree 4, then there would be no way for these to be isomorphic. So we construct the degree sequence here. We get a 4, 3, 3, and again 2, 2. All right, so claim, it is a necessary condition for two graphs to be isomorphic that they have the same degree sequence. All right, and then they could have the same degree sequence and yet not be isomorphic. Please draw me two graphs with 5 vertices which have the same degree sequence but are not isomorphic.
You want us to draw
Non-trivial, as judged by me.
Please put two edges down.
I don't know, just like, give an example. Yeah, let's keep it simple. I think, I don't know. Yeah, see if we can do a simple one. I didn't like prepare this or anything. Anyone successful? You're successful.
Excuse him, do that.
Don't do that again. No idea what I'm doing. What's yours?
This one is a triangle.
Yeah, but
Was I
Wait.
wrong about the degree symbols?
I don't know. I'm confused.
It's like, this one makes 3 go out, this one also makes 3 go out. Then this one.
Let's draw it. Wait, come draw it.
Just simple mean.
Like, you know, I don't know how far my edge is.
Yeah.
Yeah, did you like remove it back to itself? That's
Yeah, no,
that's
you're
really
really
good.
good.
Yeah. 2, 2, 1.
Oh, it's basically.
Yeah. Damn. Nice.
I think that's the same as yours. though.
Yeah, it's the
Yeah,
same.
it's the same.
These are-
Good.
Yeah. I got
Okay.
one, which is-
Good job. Anna Bart says, yeah, I made 2 graphs. These are, first of all, let's confirm. They have 5, each have 5 vertices. They each have 5 edges as well. the degree sequence here is 3, 2, 2, 2, 1. Here it's 3, 2, 2, 2, 1. Yet they're definitely not isomorphic. For example, here there is a cycle of length 4, but here there is no cycle of length 4. And that's one way of saying that they for sure cannot. So that's another way of testing to see if two graphs are isomorphic. All right. So yeah, this is really awesome. Also, so having the same degree sequence is a sufficient but not necessary condition for two graphs to be isomorphic. All right. I think we should talk a little bit about computers for a minute because
necessary.
it is necessary. I said that backwards. It is necessary that for two graphs to be isomorphic that they have the same degree sequence, but not sufficient. As we sorry. Okay. Good. All right. How are computers going to do this? Because at a certain point, you'll become dumber than computers. That's when the graph has like 25 vertices or something. And just looking at it is probably not going to work. So we need some kind of actual algorithm. And can we talk a little bit about isomorphism algorithms? Someone got one off the top of their head.
Like you can make two adjacency matrices and then maybe just do like row swapping kind of thing.
Yeah, okay, so right, before we can even talk about an algorithm, we should give some attention to what it even means for, how would a computer even get a graph? How is it encoded? So one way to do this is to have an actual labeling of the edges and having a, so here's edge 1, edge 2, edge 3, edge 4, edge 5. Okay, so one thing we can do for this graph, for example, one way in which this graph could be encoded is in an adjacency matrix. But I think this is a little different from the one we did before. Now we're going to actually encode every edge and every... We didn't do this previously, did we? So A is... So edge 5, for example, is adjacent with 1, or is adjacent with A and is adjacent with B, but... Wait a second. Edge 5 is adjacent with A and B, but nothing else. Edge 4 is adjacent with C and D, but nothing else. Edge 3 is adjacent with C and E, and nothing else. Edge 2 is adjacent with B and E, and nothing else. And edge 1 is adjacent with B and D, and nothing else. Okay, so this is a matrix which captures precisely all the relationship between all the vertices and all the edges. Okay, so this is one way in which your graph could be encoded.
Why are you doing the adjacency matrix this way?
This is not an adjacency.
Yeah.
This is a different kind of matrix. This is like a, you're saying with just, well, I think this is better. I think this is better than having just whether there is an edge or not between two.
Wait. Why?
Why? Well, first of all, that information is recoverable from this.
Yes.
Yeah, but
Right?
you could also recover the other way.
I think this is better because you want, okay, but bless you. I'm just kind of speculating here a little bit, but if you guys are talking but they're not sharing, if you want to, I think if you want to code this, you kind of need some sort of actual data structure that represents the edge. Because you want to do things like count the edges and run counters on edges. You want to actually store the edges.
Just sum all the numbers in your matrix and divide by 2.
Because each one in your matrix is just an edge.
That would be even true for a
Even for a multi-graph, that would work.
Yeah, let's just.
Alright, Jesse, why do you like this better?
Just because if you did our adjacency matrix, we'd have A, B, C, D, E on rows and columns, and flipping rows, you'd also probably have to flip a column or something. But here, you just kind of flip rows and see if they're the same. Because
the nice thing with the adjacency matrix that we normally use is you could square it and you still need to get the same number.
But we don't really need that for this.
No, but I mean that would also be a way to check.
That's just a check though. It's you can already do it pretty quickly, I think.
Well, I don't know. I have not ever tried to program these algorithms or really looked at them super carefully.
Wait, I'm sorry, what are you saying? Would you swap the rows?
It's if we had A, B, C, D, E, A, B, C, D, E as rows and column headers, say we were trying to rename vertex B A, then we'd have to switch rows 1 and 2 and column 1 and 2.
I don't think there's a convenient way to do that.
Yeah, so it's better using this.
Yeah, you'd have one.
Okay, wait, take a step back. What he's saying, because none of our might know what he's even talking about. What he's saying is, first of all, doing it this way, it's totally fine to just swap columns, right? Because that doesn't change the information contained in the matrix at all. It's also possible to swap rows, right? Because all the information is there where you need it. So two graphs are isomorphic if and only if the representation in this structure is exactly the same. And so it would be if you had two matrices representing two graphs, and those matrices are exactly equivalent via any like row swaps or column swaps. And I feel like they're just like are efficient ways to swap rows and swap columns and to see if they're the same. I don't know, like
but you
super
just
key.
simultaneously swap the row and the column.
Yeah, you'd have to consider all possible like row and column swaps. And if the matrix is the same from in this way of storing it, then the two graphs would be.
You can also like either swap rows.
Then you can only do some. You only do some, right?
So
You can like always.
You can't.
We know that
you can't
vertex H has to be vertex A. This is an isomorphism.
Yeah, if you were going to actually program it, I haven't thought terribly much about this, but yeah, you could, for example, there are sort of efficient ways to do this, where you pick two vertices, there's like only one vertex here with the same, with a certain degree, and then you match it with
There's
the
no
vertex
need
with
for
the
you to
degree.
swap both the rows and the columns.
No,
Yes, because you're renaming A.
Yeah,
Why are you renaming
You're
A?
literally. I think I don't actually know how you're going to do this one. This one looks kind of hard.
Yeah.
I think the best way is with our normal agency matrix. But when you
So then changing your mind?
Yeah.
Okay, so here's like a terrible algorithm, but it's worth mentioning. Consider just consider every possible isomorphism.
Like,
Yeah.
they might be the same, but.
Right, so then I don't need to swap row. Well, actually, I'm not really swapping rows. I'm just swapping.
So to test if they're actually the same matrix, you have to do like row swap.
Because how I decided to, I think the better way to say it is you first establish the isomorphism between the vertices.
I don't know either.
And then you check to see if the matrix is the same. But consider how many possible ways of doing that there are. Like just straight up, like how many bijections are there?
Wait, the best thing to do would be like multiply by like.
But you're gonna have, if you flip a row, you have to flip a column.
What do you call those things?
Because the rows and columns are
All three
intertwined.
matrices, right? Just multiply a bunch of elementary.
You can't flip row 2 and row 4 and not row
And like.
Alright,
column
so
2 and column
I'm in a little bit over my head here, maybe you guys are too, I don't know. This is like a whole field of how to do this. And the reason is because, I'll mention this and then we'll move on. There are a freaking lot of bijections. If you want to actually find the connections, like think about what you would have to do. Like take vertex A. If you're just a computer and you're just brute forcing this, there are like 5 possible vertices which you can match to A, right? And then moving on to B, you have 4 possible vertices. So there are just n factorial, for a graph with n vertices, there are n factorial possible bijections.
I mean, the easiest way to say that is just, sometimes there's n factorial. So there might be symmetries, but.
Right, of course there are, and there are some which are going to be nonsense, but just like straight up, like at worst, you have n factorial different bijections to check. And then that's not even talking about the check
there's
itself.
n ways to like name the vertices.
There's n.
So you're just like doing n factorial.
Yes. Yeah. So it's a very efficient algorithm, and this is like has all the properties that you don't